Hi, I'm Kay Osterhout, and today I'll be talking about distributed low-latency scheduling with Sparrow. Sparrow schedules tasks for jobs running in compute clusters using a decentralized, randomized approach. This approach avoids the throughput and availability limitations of today's centralized schedulers, and in doing so, loses very little. Sparrow can support policies and constraints and provide response times within 12% of what an ideal scheduler could provide. In this project, we look at scheduling in large-scale compute clusters. These are clusters with anywhere from hundreds to many tens of thousands of machines. We're looking particularly at scheduling for data analytics frameworks. These are things like MapReduce, Spark, and Dryad. A typical job in one of these frameworks is composed of some number of parallel tasks, and the scheduler's job is to assign each task to one of the machines. The scheduler does this not just for one job, but for many jobs that are running concurrently. Now, if you look at the duration of jobs running in these clusters, there's been a big change over the past decade or so. When people first started running this type of job, they used frameworks like MapReduce, and the typical job took many hours to complete. But ever since the early days, there's been a drive to push down latencies, to still analyze large volumes of data, but to return a result to the user very quickly. This has led to innovations in the query frameworks with things like Hive, improved data layouts, and striping work over many more parallel tasks using things like Dremel, and most recently doing aggressive caching of data in memory with frameworks like Spark. At the cutting edge, the fastest data analytics frameworks can analyze large volumes of data and still return a result to a user in hundreds of milliseconds. This is a trend that we expect to continue going forward. Now, these very short jobs pose some major challenges for task schedulers. The first challenge is that the scheduler is going to need to provide millisecond scale scheduling latency. Otherwise, the scheduling latency becomes a significant component of job completion time. The scheduler also needs to provide quality placement decisions. We mean a couple of different things by this. First of all, many of these jobs achieve low latency by striping work across hundreds or thousands of parallel tasks. The scheduler needs to place all of these tasks on machines where they won't have to wait a long time before being run. Even one task placed on a machine where it has to wait a while will slow down the completion time of the entire job. The scheduler also needs to provide quality placement in the sense of satisfying constraints and satisfying fairness policies across many users using the cluster. A third challenge is fault tolerance. As these jobs get shorter and shorter, they're becoming fast enough to power user-facing services, which will make fault tolerance increasingly important. And the final requirement is high throughput. When jobs are very short, there's a very high rate of task turnover in the cluster, and so the scheduler needs to make new task scheduling decisions quite frequently. If you look at the combination of these challenges are becoming increasingly difficult to meet with today's centralized scheduler designs. To look at a particular one of these challenges, let's look at the throughput needed to support a modestly sized cluster that has 1,016 core machines. Back when jobs took tens of minutes to complete, a centralized scheduler only needed to provide tens of task scheduling decisions per second, something that was easily attainable. But as these jobs get shorter and shorter, the scheduler needs to provide more and more task scheduling decisions per second. To look at where one particular one of today's centralized schedulers falls along this continuum, the Spark scheduler can perform about 1,500 task scheduling decisions per second. And what you can see here is that there's already a gap. There's already about a 2 order of magnitude difference between the shortest latency jobs Spark can support and the throughput of scheduling decisions that it can make. Of course, you could design a centralized scheduler that provides higher throughput than this, but there's going to be some limitation. There's going to be some throughput at which a centralized scheduler can no longer keep up. Returning to this list of goals, we've talked about why high throughput is difficult to provide with today's centralized scheduler designs. It's also difficult for a centralized scheduler to provide low latency. Many of today's centralized schedulers improve throughput by batching multiple job scheduling requests together, but this harms latency. It's also difficult for a centralized scheduler to provide fault tolerance. Doing fault tolerance requires doing things like replication and checkpointing that are very difficult to do once at a 100 of millisecond level scale when these jobs are very short. Now, there's one big advantage of centralized schedulers, which is that they have global visibility. This enables them to do a good job of placing tasks. They have a view of the tasks that are running on all of the worker machines in the cluster, so they can make sure that all of the many tasks in a job are placed on machines where they won't have to wait for a long time. They can enforce constraints, and they can also enforce global policies across many users. However, the sum of all of these goals is going to be increasingly difficult to support with a centralized scheduler. To meet the demands of low latency workloads, Sparrow takes the opposite extreme in the design space and schedules from a set of schedulers that are completely decentralized. This gives us a lot of advantages over a centralized technique. Sparrow can provide higher throughput by adding additional schedulers. It can handle scheduler faults because there's many schedulers running in parallel, and it doesn't have this issue where it needs to do batching that harms latency. The big question is, can Sparrow continue to provide quality placement? Can we avoid multiple schedulers operating in parallel, making conflicting decisions? Can we still enforce job and task constraints? And can we still enforce policies across many users running in the cluster? In this project, we answer this question with a yes. Sparrow can provide near optimal response time, can support constraints, and can also enforce the most common types of policies across many users. It does this all without any global visibility. In the rest of this talk, I'll begin by talking about Sparrow's randomized approach. I'll talk about why some existing approaches don't work, and then I'll present the two key techniques underlying Sparrow, batch sampling and late binding. In the paper, we also demonstrate analytically that these techniques perform well. Next, I'll talk about how Sparrow can handle constraints in its decentralized framework. In the paper, we also demonstrate how Sparrow can enforce policies in spite of the fact that schedulers don't have any global visibility. Of course, we do give up something here by having a decentralized design. There will always be some policies that Sparrow can't support because the policies require some kind of global visibility. What we show in the paper is that Sparrow can support the most common types of policies that people use. Finally, I'll end with an evaluation of Sparrow on a 100-machine cluster, and I'll demonstrate that Sparrow can provide response times within 12% of what an ideal scheduler could provide. First, Sparrow's approach. When a job arrives at a Sparrow scheduler, it has no prior knowledge about what's going on in the cluster. It has no information about what's running on any of the worker machines, and there may be many other schedulers operating in parallel that this scheduler doesn't know about. We'll model each worker machine as a queue, so each worker can run some number of tasks at a time, and if it's assigned more tasks than that, it will add them to the queue. Now, how can we possibly do a good job of scheduling? One thing that we know that can provide good performance in this type of decentralized environment is using randomization. If we randomly assign all of the tasks to worker machines, we know that in aggregate, all of the workers will be assigned the same amount of work. And indeed, this randomized approach performs well at low load. What we're looking at here is simulated results in a cluster with 10,000 machines where each job has 100 tasks. We're comparing the random approach to an omniscient scheduler, where you can think of the omniscient scheduler as a centralized scheduler that's infinitely fast. So it schedules based on global visibility, but it doesn't have any of the latency or throughput limitations that a real centralized scheduler would have. What you see here is that the performance of this random approach essentially maps perfectly to the omniscient scheduler at low cluster load, but as load increases, random starts to move pretty far away from an omniscient scheduler. Now, one approach that's been used in environments like load balancing web requests is this technique called the power of two choices. The idea of the power of two choices is that you can get a lot by having just a little bit of additional information. So when the scheduler is placing a task, instead of just randomly picking a worker machine, let's sample two worker machines. They'll both reply with what their load is currently like, and the scheduler places the task on the worker machine with the shorter queue. To directly apply this technique to parallel jobs, we simply do the same scheduling for each of the tasks in the job, and we call this approach per-task sampling. And as I mentioned, this is something that's used in a variety of different environments today. Per-task sampling improves performance over random, but nonetheless is quite far from an omniscient scheduler at high load. It turns out the problem is a little bit worse than it looks like from this graph. If you instead look at the response time for jobs as the number of tasks in the job increases, per-task sampling does worse and worse. As the job becomes more parallel, intuitively the problem is that with each additional task, there's increased probability that at least one of the tasks in the job will have sampled two machines that are both heavily loaded. that task will have to wait a long time, and it will slow down the entire job. Now, the whole point of this project was to get good performance for these parallel workloads. So how are we going to be able to get around this problem? This is where the first of the key techniques underlying Sparrow's approach comes in. It turns out that we can make this very small change to per-task sampling that yields a massive improvement. Looking back at what happened with per-task sampling, we scheduled these two different sets of worker machines. But if you look at what happened here, both of the worker machines sampled by the second task are less loaded than the two worker machines sampled by the first task. We ended up not using this circled worker, but we could have improved performance if we had shared information across all of the probes in the job so that we could utilize those two least loaded workers. And this is exactly what we do with batch sampling. So the idea of batch sampling is instead of probing individually for each task, we send a single batch of probes for all of the tasks in the job, and we place the job's tasks on the workers from that entire batch that have the shortest queues. You can see that batch sampling does not suffer from the same tail problem that per-task sampling suffers from. As the number of tasks in the job increases, the response time doesn't increase significantly with batch sampling, unlike with per-task sampling. Unfortunately, if we look at the results as load increases, batch sampling is still quite far away from an omniscient scheduler at high load. There's a couple of different problems remaining with batch sampling, but the biggest problem is that queue length isn't necessarily a good predictor of wait time. If you consider a scenario where the scheduler probes two worker machines, one with two tasks in the queue and one with just one, the scheduler will place the task on the worker with the shorter queue. But the scheduler had no way of knowing how long these tasks would take. It could be that those two tasks were both short and the one task is long, and the job would have had to wait less if the task had been placed on the worker with the longer queue. As a result of this property, batch sampling performs worse and worse as workloads get more heterogeneous, and we know that heterogeneity is a common property of today's cluster workloads. So how can we solve this problem? How can we deal with this gap in information? One thing you may be wondering is, why are we returning the length of the queue? This seems sort of stupid. Why don't we try and make some prediction based on history about how long each of the tasks are going to take? And again, we're really hurt by the parallelism in a job. If you have a job that has 100 tasks, you need to have 100 accurate estimates for that job to have a low response time. You need to accurately predict the queue length on each queue where one of the job's tasks is placed. And given the presence of things like stragglers, no one's been able to do prediction with this level of accuracy. So to solve this problem, Sparrow introduces late binding. And the idea of late binding is that we're going to delay the assignment of tasks to worker machines until we know exactly how long they'll have to wait. Again, when a job arrives, the scheduler sends probes to worker machines, but the workers queue the probes. They don't reply immediately. If we focus on this top worker, the worker processes work over time, and eventually the probe for this job reaches the front of the machine, reaches the front of the queue, and the worker has available resources on which to run the task. Only then does the worker machine request the task from the scheduler. So the scheduler holds on to the tasks until one of the worker machines indicates that it's ready to run it. In this approach, we guarantee that the tasks will be run on the machines among the probed workers where they'll run the soonest. Late binding significantly improves performance. At up to 80% load, late binding provides response times within 5% of what would be provided by an omniscient scheduler. Now, so far I've talked about a simplified environment where tasks can be placed on any worker machine. But how can we handle constraints? Sparrow can handle a couple of different kinds of constraints. The first is job-level constraints. This type of constraint arises when all of the tasks in the job need to be placed on a machine with a particular property. For example, all of the tasks in my job need to be placed on a machine with a GPU. Here, all of the tasks in the job need to be placed on a machine with some diamond property. Sparrow can trivially handle this type of constraints. Rather than randomly selecting the workers from the entire cluster, Sparrow selects the workers to probe from that set of workers that satisfy the particular constraint. Sparrow also handles per-task constraints. These kind of constraints commonly arise in data analytics frameworks because the tasks in the first phase of a query should run on a machine where the input data resides. Sparrow handles this type of constraint by probing individually for each task. So in this job, for the first task that has some pink triangle constraint, Sparrow sends 2 probes to machines that satisfy that constraint, and the same thing with the blue circle constraint. You'll notice that with these per-task constraints, Sparrow can no longer use batch sampling. but we can still use late binding. And if you look at what's happening here, if we had a centralized scheduler would only have had information, say for the pink triangle task, about a total of 3 machines. This magical number 3 happens a lot because typically these constraints arise because tasks are reading input data from one of 3 replicas, which is the most common number of replication used in today's distributed file systems. So a centralized scheduler would only have had information about 3 choices for where to place the task. And Sparrow gets complete information about 2 of those choices. So in the case where jobs have per task constraints, the information gap between what Sparrow knows and what a centralized scheduler would know is actually much smaller. To recap, I've presented Sparrow's randomized technique. I've talked about the 2 key techniques underlying this approach, batch sampling and late binding, and I've also shown how Sparrow can handle constraints. Now let's talk more about how Sparrow performs on a real cluster. So far I've just shown simulation results. To evaluate Sparrow on a cluster, we ported Spark, an in-memory data analytics framework, to schedule using Sparrow. A Spark query is composed of a DAG of stages. Spark submits each one of these stages as a job to Sparrow. Sparrow schedules the tasks in the job. Once they complete, Spark submits the next job to be scheduled using Sparrow. And same thing for the remainder of the stages. So the response time of a Spark query run using Sparrow is the sum of the response times of some number of sub-stages in that query. The other thing you'll notice here is that there's this Spark executor running on each one of the worker machines. This executor already has a JVM up and running where it can run newly arriving tasks, and this is necessary to provide low latency. If we had to start a new executor and ship a large binary for each task, Sparrow wouldn't be able to have tasks complete in hundreds of milliseconds. And this is an approach used by a number of schedulers, including Mesos. So the information that Sparrow sends when it launches a task is just this much shorter functional query definition. At the beginning of this talk, I mentioned that Spark scheduler has a throughput limitation of about 1,500 tasks per second. So this graph compares Sparrow to Spark's native scheduler using a simplified workload. This is running on a cluster with 100 machines, and each job is composed of 10 tasks that all have the same duration. So as we decrease the duration of a task from, say, 4 seconds to 2 seconds, we expect the job response time to correspondingly decrease because all of its tasks are the same length. And indeed, Sparrow, which here is using 10 schedulers, follows that ideal line perfectly. Spark, on the other hand, hits this bottleneck at once tasks cross about 1,300 milliseconds, where jobs are being submitted much more quickly than the scheduler can keep up with. The scheduler starts experiencing infinite queuing, and job response times approach infinity. So Sparrow is necessary to support these lowest latency queries. Now, how does Sparrow perform on a more realistic workload? This is just the synthetic queries where all of the tasks are the same duration. To look at Sparrow's performance on a more realistic workload, we ran a bunch of TBCH queries, and we ran this using Shark, which you can think of as essentially just SQL query analytics on top of Spark. This graph compares Sparrow, which uses batch sampling along with late binding, to a couple of alternative techniques. And there's a number of takeaways from this graph. The first is that we get an improvement both from doing batch sampling relative to late binding, and then we get an additional improvement, batch sampling relative to per task sampling, and then we get an additional improvement from doing late binding. So Sparrow really needs both of these techniques in order to provide good performance. The other takeaway here is that Sparrow improves median response time by quite a bit compared to per task sampling, the best prior technique, but it also improves 95th percentile response times by as much as a factor of 2. Now, it's nice to see that Sparrow does well compared to some alternative techniques, but how well might a perfect scheduler do? Are we leaving a lot of performance on the table still? To evaluate this, we compare Sparrow to an ideal scheduler. So the problem here is that we don't actually have a scheduler that we can use that handles these types of workloads. So instead what we do is we compare Sparrow to an aggressive ideal where there's no scheduling delay and where tasks are shipped to worker machines instantaneously. So in other words, this ideal is just the longest task of any of the tasks in a job. And nonetheless, even though this is a pretty aggressive ideal, Sparrow performs within 12% of the median response time provided by the ideal scheduler with a median queuing delay of 9 milliseconds. Another nice property of Sparrow is that it provides fault tolerance. Here we're using 2 Sparrow schedulers with 2 Spark clients. Both Spark clients are initialized to start using their own scheduler, but they're also initialized with a set of schedulers to fail over to in the event that their scheduler fails. At 20 seconds into the experiment, we kill the scheduler running on the first client, And the Spark client uses a simple timeout to determine that the scheduler has failed. Within 100 milliseconds, this timeout expires. In 5 milliseconds, it fails over to the second scheduler. And within 15 milliseconds, it resubmits all queries that were outstanding at the scheduler. This entire failover happens in less than 150 milliseconds, and as a result, only 2 queries were in flight during the failure. So there's an almost negligible impact on job response time as a result of the scheduler failing. Now, I'd like to end with a discussion of when Sparrow doesn't work as well. This graph is a blow-up of Sparrow using batch sampling with late binding of the simulation results from earlier. Sparrow maps almost identically to the omniscient scheduler until the cluster reaches high load, until load gets to be 90 or 95%. The reason for this is that high load is where you really need global visibility. There aren't a lot of choices for where to run a task, and you need to have this more complete information about what's going on in the cluster in order to find the free slots in which to stick a new job. Now, for most of the people we've talked to, it's uncommon for anyone to be running a cluster at this high of load. The more common scenario is that folks are running the cluster at a lower load on average, so that this won't be an issue. The other takeaway is that if you're running at high load, you don't have a lot of good choices. If you use a centralized scheduler, it just falls over because the throughput can't keep up. So one way to think of Sparrow here is that it's providing graceful degradation in the case of high load. It doesn't do as well as high load, but at least it schedules all of the tasks in the job. Now, there are some other regimes in which Sparrow doesn't perform as well. There are some types of policies that Sparrow has a hard time handling because it doesn't have global visibility, and we talk more about those in the paper. There's a ton of related work in this space, and I'll just touch on a couple of things here. The first category of related work is centralized task schedulers. This is something like Quincy that does similar functionality to Sparrow. It does fine-grained task scheduling, but it does so from a centralized machine. Schedulers like Quincy can provide much more sophisticated functionality than Sparrow. Quincy uses a sophisticated graph solver to determine the optimal placement of a job, but as a result, they have throughput and latency limitations that make them unsuitable for these very short task workloads. There are also a couple of schedulers that use a 2-level scheduling design. These are things like Mesos and Yarn, where there's a centralized scheduler that is the ultimate gatekeeper for all of the resources in the cluster, but they delegate some of the functionality, like determining which slots are acceptable for which tasks, to application-level schedulers. These schedulers still rely on a centralized design, and as a result, can't handle the lowest latency workloads. A third category of schedulers is coarse-grained cluster schedulers. These are things like Google's Omega. These schedulers are designed to allocate resources at coarse granularity, to allocate resources for an application that does its own task-level scheduling. They can enforce many different complicated types of policies. Omega, for example, can do very sophisticated placement that takes into account different failure regimes, but they're not designed to work at the latency of hundreds of milliseconds because they're designed for this much more coarse-grained allocation. The final category of work, and the stuff that's most similar to Sparrow, is work on randomized load balancing, used in things like web architectures. These approaches are focused on an environment where you just have to schedule a single task, and as a result, they're not suitable for these parallel workloads. Tail performance is still too high to be used on these jobs that are composed of hundreds or thousands of parallel tasks. In today's talk, I've demonstrated that with Sparrow, global visibility is not necessary to provide good performance. Sparrow's randomized approach combines 2 techniques, batch sampling and late binding, and can also support constraints in order to provide response times within 12% of what an ideal scheduler could provide without the throughput and availability limitations of a centralized design. All of our code is publicly available online, including the code to run all of our simulations. And with that, I'm happy to take any questions.
Very nice work. I'm Kai. One net difference from your name. And there are a bunch of work on queuing analysis, which shows that the job response time depends heavily on the characteristics of the workload, as well as the scheduling discipline for each queue. So could you say something more about the workload for your experiment setups? Thanks.
Yeah, so when we first started doing Sparrow, we were just using batch sampling, and we saw exactly this effect, that it depended a lot on the workload. If you had a workload that wasn't very heterogeneous, it worked quite well. And the nice thing about using late binding is it makes Sparrow much more robust to different workloads. Sparrow can still find the places where jobs will launch soon because it avoids needing to predict queue length.
So
We also did some experiments where we looked at, sorry, let me pull up this slide. Oh, this is backwards. Well, okay, so we also did some experiments where we looked at running a workload with two different types of tasks, some that were quite short and some that were quite long, to see if when you have really long tasks, does it hurt the response time of the shortest tasks. And it turns out that if you have almost all of your jobs are long, if 90% of your resources are used on jobs that are 10 seconds or more, you will hurt response time for jobs that are 100 milliseconds. But you have to have this sort of extreme amount of heterogeneity to have that kind of problem.
I see. What I'm concerned is about the
No follow-ups.
We have a lot of questions, so let's try and keep the questions short. Here's one from the moderator. How does your scheduling approach differ from, compare with, workers simply pulling tasks from schedulers? What if the constraints include completion deadlines for jobs?
Yeah, so we've actually looked at pulling tasks from schedulers using work stealing. So one thing you can do is when workers are free and they're not doing anything, they can start asking random schedulers if they have additional work. And it turns out that if you use work stealing, you can bring down the response times at 90 or 95th percentile load to be essentially optimal. The problem is that it's difficult to do only work stealing. We'd like to support an environment where you can run a large number of schedulers. And when there's, say, 1,000 schedulers running in a cluster, it's difficult for workers to know exactly which schedulers they should pull work from.
Hi, Michael Izard from Microsoft Research. So the original Dryad scheduler had some similarities to this. It would schedule on 3 machines, and then the one that won, you just shoot down the other ones. And we did Quincy because we found some problems with that. And one of the issues is that Quincy was able to revoke work and move things to better places, which I don't think this kind of approach supports very well. And so when you compare against the ideal job, have you considered comparing against ideal schedulers that use more sophisticated policies rather than just ideal ones that can only see this kind of visibility?
Yeah, that's something we haven't done much of. So it sounds like what you're talking about is supporting policies like doing priorities or something, where if you have a low priority job that's running, you might want to move it someplace else so that a high priority task can run.
Right, or if you have something with a large amount of data that needs to read, it may get, you may want to move it when that machine becomes available. But
yeah, so that's something that we haven't looked at much, and it would be interesting to explore more.
Thanks. From this side again.
Bill Tetzloff, IBM Research. Could you put this in the context, or vice versa, of Mitzenbacher's power of 2 work at Berkeley about 15 years ago?
Yeah, so the per task sampling, this is exactly the power of 2 work. And I should mention that I think the first folks to do it were actually some folks at UW, but Mitzenbacher just popularized it. But yeah, this is the per task sampling approach that I mentioned at the beginning. That's exactly Mitzenbacher's power of 2 choices.
I'm Sriram from Microsoft. Very nice work. The focus of this work seems to be more on providing throughput or improving the scheduler's throughput. How does this, how do you handle fairness constraints in your setup?
Yeah, let's see if I can successfully pull up this slide this time.
In the interest of time.
Yeah, so the way that Sparrow supports fairness is we do something very simple, where each of the workers do weighted fair queuing over some number of queues. So if you just have 2 users, each worker maintains 2 queues, and they do weighted fair queuing over those queues. And it turns out that this simple approach actually works quite well when you don't have a ton of workers. And so that's how Sparrow can enforce fairness constraints. And we have some results in the paper showing that this works well. You don't get perfect fairness because it's sort of this aggregate fairness where you may have fluctuations in the short term, but in aggregate you can still get weighted fair shares.
Thank you. I guess since I don't have follow-up,
No follow-ups.
I'll follow up with you offline.
No follow-ups. Another question from the moderator. How does Sparrow handle heterogeneous clusters with competing workloads? For example, jobs might contend for GPU resources, but be okay with scheduling on CPUs. They will just take longer. And then I think we're going to take Ken, and that's probably it.
Yeah, so one thing we've looked at in this type of environment is doing something like delay scheduling. So where you would first send a bunch of probes to the types of workers that are the sort of first choice workers, so in this case the workers with GPUs, and then if nothing becomes available within some short time window, we would open up the set of probes the scheduler sends. It would send a bunch more probes to workers that satisfy this more general sort of second choice set of requirements. We haven't explored this much, but we think it's something that would work quite well.
Ken Berman, Cornell. So it seems to me that with very short jobs at high load, you're going to get a situation where the probe load becomes very dominant, and in fact, doesn't give you that much value because your work is responding to many schedulers in parallel. Does it make sense to start to move towards something where the workers would periodically inform the schedulers, and you would skip the demand aspect of probing at that point?
Yeah, that's a good question. And we did some experiments where we varied the probe ratio at high load, and we saw exactly what you mentioned, that if you use a high probe ratio, at some point it actually starts to hurt you because the machines are dealing with all of these extra messages and they end up taking longer. And one thing you can do if you anticipate in general running at high load is just use a lower probe ratio. It turns out if you use a ratio of like 1.1, so you're just doing 10% extra sampling, it can still do quite well. The problem with trying to do some dynamic adjustment of this is it's very difficult to configure. It's hard to know the difference between when a scheduler just got unlucky and sampled a bunch of bad machines and it should probe more compared to where the cluster is more highly loaded. So we weren't able to come up with a good way of doing that.
Okay, thanks. Very nice talk.
All right, let's thank our speaker again.